Okay, so this lesson is from section 6.5 in the textbook and on inverse trig functions. And I'm going to break this video into two parts because it is a longer section. So we've already studied inverse functions. Remember back in first semester at the end of chapter 1, when I introduced inverse functions, I drew you guys the picture of the function machines. So like if this is a function named f, and let's say that this is that function's inverse. If I were to input a value into the function f, like let's say I input 2 and get out 5. If I were to take 5 and input it into f inverse, the output would end up being 2. Okay? So for a function to have an inverse and for a function to be an inverse of another function, it must be a one-to-one function. And one-to-one functions means that every input corresponds to exactly one output and every output corresponds to exactly one input. So graphs of one-to-one functions will pass both the vertical line test as well as the horizontal line test. The vertical line test, if a graph passes the vertical line test, just means that it represents a function. And then if that graph also passes the horizontal line test, it means that the function is a one-to-one function and therefore will have an inverse. The domain and range, and this can be seen in my little picture of the function machines, but the domain and range is flip-flop for a function in its inverse. So the domain of f inverse is the range of the function f, and the range of f inverse is the domain of the function f. Also going off of that, just the definition of what it means to be an inverse function is if we compose the equations of f inverse in f and f inverse, both directions, so f inverse composed with f of x and f composed with f inverse, both of those compositions should simplify to just be x. And that's because if we're thinking about evaluating f inverse at all of the outputs, so all the values in the range of the function f of x, that means that the outputs of f inverse will be the inputs of f of x. Okay, and then the same way composed, so if we evaluate f of x at all of the outputs of f inverse, then the outputs of that composition would be all of the inputs of f inverse. And that's also why we specify for all x in the domain of whichever the inside function is. Now, the trig functions. We've just studied the trig functions, all 6 trig functions. Here are their graphs. You can pause right here, and it might be a nice little review to go ahead and sketch the graphs of all 6 trig functions, the parent functions, without looking at my graphs. Just nice little review. But we know that the 6 trig functions are all periodic functions. If we think about their graphs over their implicit domain do not pass the horizontal line test, right? Like for the graph of sine of x, if I draw a horizontal line, that horizontal line is going to end up hitting the graph of sine in infinitely many places. Get rid of that one. The thing is, the trig functions do have inverse functions. And the way that works is by restricting the domain of each of the 6 trig functions so that each of the trig functions is a one-to-one function. So for sine, we want to make sure that we get all of the possible values in the range of sine in each of the functions for when we restrict their domain. and we end up restricting the domain kind of as close to the origin or about the origin as possible. So in order to make sine a one-to-one function, we're going to restrict the domain to be from, here, let me use the highlighter, from negative pi over 2 to pi over 2. Notice we get, remember the range for sine is from negative 1 to 1, and from x equal to negative pi over 2 to pi over 2, we end up getting all of the values that are in the range of sine. So to restrict the domain for sine, this is going to be the restricted domain. It's going to be from negative pi over 2 to pi over 2. That makes sine 1-to-1 on that interval. And then the range is still negative 1 to 1. Okay, for cosine, well, if we use that same interval from negative pi over 2 to pi over 2, notice on that interval, cosine would not pass the horizontal line test. However, from 0 to pi, we get all of the outputs for cosine between negative 1 and 1. And on that interval, cosine would pass the horizontal line test. So the restricted domain for cosine, forcing cosine to be 1-to-1, will be from 0 to pi. And the range still from negative 1 to 1. Tangent is pretty easy to see. Tangent, just between negative pi over 2 and pi over 2, right, which actually ends up being one period of tangent. Tangent over one period is 1-to-1. So the restricted domain for tangent will be from negative pi over 2 to pi over 2. Notice that at negative pi over 2 and pi over 2, there's vertical asymptotes, because remember, tangent is undefined at negative pi over 2 and pi over 2. So we will use parentheses to represent the domain, the restricted domain for tangent, and the range is all real numbers. Okay, cosecant and secant are a little bit more challenging to see how we would restrict their domains. Now, if we tried to use an interval that included an entire U shape, then the graph would not pass the horizontal line test. So we're actually going to restrict the domain of cosecant to be from negative pi over 2, because then we'll get part of a downward facing U, to pi over 2. And we can't forget that cosecant is undefined at 0. Okay, so on that interval, it looks funky, but it has all of the values that are in the range of cosecant, and that graph would pass the horizontal line test. So the restricted domain for cosecant, why did I write it R, would be from negative pi over 2, and negative pi over 2 is included in that interval, to 0. Okay, and we need to exclude 0 because at 0, cosecant is undefined, and then up to pi over 2, and we will include pi over 2. And the range, reading from bottom to top, would be negative infinity to negative 1, union 1 to infinity. And I'm just missing my labels on my y-axis there. Okay, same idea for secant. We need part, basically half of an upward facing U and half of a downward facing U, but close to the origin. So we're going to use from 0 to pi. Okay, so the restricted domain of secant will be 0. And then we have to exclude pi over 2 because secant's undefined at pi over 2 up to pi. The range, like cosecant, will be negative infinity to negative 1, union 1 to infinity. Okay, cotangent, like tangent, one period is really, so in this case from 0 to pi, or the interval between the vertical asymptotes is 1 to 1, right? Would pass the horizontal line test. So for cotangent, our restricted domain will be from 0 to pi. And again, I'm not including the end points of the interval. So I'm not including 0 and pi because there's vertical asymptotes there. Cotangent's undefined at 0 and pi. And then the range would be negative infinity to positive infinity. So we're going to look a little bit closer at inverse sine, inverse cosine, inverse tangent right now. And then in the second part of section 6.5, so the second video, we'll take a little bit deeper look at the other 3 inverse trig functions. Okay, inverse sine. So we inverse sine, the equation of inverse sine. I have it written down here. The 2 different notations. Okay, so that first equation is not sine. I know that it can be confusing because we use the notation for like sine squared. That's equal to sine, right, raised to the second power, or which is sine times sine. However, the notation here, that is not sine raised to the negative first power, or 1 over sine. It means inverse sine. So it's sometimes easier to use arc sine, but you should be familiar with both notations. So we have 2 different, and you can use either one, but you should be familiar with both. So y equals to inverse sine or y equals to arc sine means x equals to sine of y, where y is the angle measure whose sine is equal to x. So I like to think of it as the inputs for y equals arc sine are ratios and the outputs are angles. Okay, because for y equals sine of x, the inputs are angles and the outputs are ratios. Okay, so for the inverse, the inputs would be those ratios and the outputs would be the angles. Oh, sorry. No. Sorry, the inputs would be the ratio and then the outputs would be the angles. Or I'll just write it out here. So if we have y equals to arc sine of x, okay, the inputs here will be the ratios that sine is equal to. And then the outputs will actually be the angles. Okay. Now, so going back up here to sine, the domain over which sine is 1 to 1 is negative pi over 2 to pi over 2, and then the range of sine is negative 1 to 1. Remember, for inverse functions, the domain and the range flip-flop. So that means that the domain of inverse sine is negative 1 to 1, and the range is negative pi over 2 to pi over 2. So on the unit circle, and this helps me for when I'm thinking about, because I think about the unit circle in order to evaluate sine for exactly for angles on the unit circle, or for, so for evaluating exactly, here, let me draw my unit circle. Okay, so the range negative pi over 2 to pi over 2 would be quadrant 4, right? Negative pi over 2 to 0, and then 0 to pi over 2 would be quadrant 1. Okay, so basically inverse sine is going to give you angles. When you evaluate inverse sine, you're going to get as outputs angles between negative pi over 2 and pi over 2, which are angles from quadrant 1 and quadrant 4. So if you evaluate inverse sine at a negative ratio, sine of those two quadrants, sine is negative in quadrant 4. So if you're evaluating inverse sine at a negative ratio, like let's say negative 1, okay, inverse sine of negative 1 would be equal to negative pi over 2. Or how about negative root 2 over 2? So inverse sine of negative root 2 over 2 would be equal to negative pi over 4. Right? I'm thinking on that interval from negative pi over 2 to pi over 2, where would sine be equal to negative root 2 over 2? And that would be at negative pi over 4. Inverse sine of 0 would be equal to 0, right? Because sine of 0 is equal to 0. And then for when we evaluate inverse sine at positive ratios, like root 2 over 2, inverse sine of root 2 over 2 will be pi over 4. So from quadrant 1. And inverse sine of 1 would be equal to positive pi over 2. So the graph here, I'm going to graph inverse sine by hand. The other ones I think I'm going to skip graphing by hand, but I will show you on Desmos what they look like. So let's say that this is negative 1 and this is 1, right? Because our domain is from negative 1 to 1. And that would mean negative root 2 over 2 would be about there. Positive root 2 over 2. Okay, and then I'm going to say that this is positive pi over 2, which means this is pi over 4, negative pi over 4, negative pi over 2. Okay, so graphing those points, negative 1, negative pi over 2, negative root 2 over 2, negative pi over 4, 0, 0, root 2 over 2, comma pi over 4, and then 1 pi over 2. So that's the graph of inverse sine or arc sine. Let me show you with Desmos. Oops, let's see if I can make this work. Let me show you with Desmos, because remember that the graphs of two functions that are inverses of each other are symmetric about the line y equals to x, since those domains and ranges are switching. So notice Desmos uses inverse sine, that notation with the negative 1. Okay, so if I zoom in, that looks pretty close to what we graphed by hand. And notice if I were to graph sine, Okay, sine would be, I would need to restrict the domain. I'm trying to think, remember how to do that. Negative pi over 2. Does that work? Nope. Okay. I can't remember how to restrict the domain on here. But, so from negative pi over 2 to pi over 2, you can see if I were to draw the line y equals to x, that the graph would be, they would be reflections of each other over the line y equals to x, or symmetric about the line y equals to x. Okay. So let's think about finding the exact value of each of the following expressions. So these expressions actually, when simplified, represent angles. And like I said, I like to think about the unit circle when I'm trying to evaluate the inverse trig functions. Just like I think about the unit circle, I visualize the unit circle. When I'm evaluating the trig functions at angles, I think about the unit circle when I'm evaluating the inverse trig functions as well. Let me draw a unit circle just as reference. Okay. So remember, inverse sine is going to give us angles from quadrant 1 and quadrant 2. Because that is the restricted domain for sine, which makes sine a one-to-one function and therefore have an inverse. All right, inverse sine of negative root 3 over 2. Well, sine is negative in quadrant 4, right? And I'm thinking, okay, well, what angle in quadrant 4 between negative pi over 2 and pi over 2? So from quadrant 4, which angle would give me sine equal to negative root 3 over 2? Right, so this point right here would be 1/2 comma negative root 3 over 2. That angle, right, it would be the negative angle would be negative pi over 3. It would be incorrect to say the coterminal angle, so the positive angle between 0 and 2 pi, it would be incorrect to say 5 pi over 3. Because 5 pi over 3 is not in the range of inverse sine. So inverse sine of negative root 3 over 2 is only equal to negative pi over 3. And if you were to type that into your calculator, if you're in radian mode, it'll give you the approximation of negative pi over 3. If you were in degree mode, it would give you negative 60 degrees. All right, arc sine of 1/2. Well, okay, sine is positive in quadrant 1, and sine would be equal to 1/2, approximately there, right? So that point is root 3 over 2, comma 1/2, and that angle would be pi over 6. Okay, so arc sine of 1/2 is equal to pi over 6. Okay, let me do one more example just to kind of get the point across. So about like inverse sine of negative root 2 over 2. Okay, sine is negative in quadrant 4. Okay, at approximately that point, that would be the point root 2 over 2 comma negative root 2 over 2. That angle which is in the range of inverse sine. So between negative pi over 2 and pi over 2 would be negative pi over 4. So not its coterminal angle, only negative pi over 4. Okay, so this just goes back, these identities, so they're called the sine inverse sine identities, just go back to the definition of inverse functions. So if you compose inverse sine with sine, that simplifies to x for the domain of the inside function, which, remember, the domain for sine being 1 to 1 is between negative pi over 2 and pi over 2. So this is pretty common sense. You could think about it, inverse sine of any ratio between negative 1, inverse sine of any ratio between negative 1 and 1, which sine is only going to give you outputs between negative 1 and 1 since that's its range, are going to give you angles between negative pi over 2 and pi over 2, because that is the restricted domain for sine to be 1 to 1. And same thing here. So if you're evaluating sine at inverse sine of x is going to give you an angle, and it would be an angle between negative pi over 2 and pi over 2, then the output of sine composed with inverse sine will be a value between negative 1 and 1. And negative 1 and 1 is the domain of inverse sine. Okay, so that identity really just uses the definition of inverse functions. All right, so let's find the exact value for each of the following trig expressions. Okay, and sometimes we'll be able, it can be kind of if you recognize that it's the case of what this identity is saying, it's a little bit faster to evaluate. So sine evaluated at inverse sine of negative 1/2. Well, inverse sine of negative 1/2 is going to give you a negative angle from quadrant 4. So that angle would be negative pi over 6. So this is actually equal to sine of negative pi over 6, which is equal to negative 1/2. So this follows this second identity here, where since inverse sine is being evaluated at a value between negative 1 and 1, the identity holds here. So sine of inverse sine of negative 1/2 is equal to negative 1/2. Okay, looking at B, inverse sine of 5 pi over 6. Well, 5 pi over 6 is in quadrant 2. Sine of 5 pi over 6 is equal to 1/2. So inverse sine, this is equal to inverse sine of 1/2. And inverse sine of 1/2, well, that's going to actually be equal to pi over 6. So the identity does not hold here because 5 pi over 6 is not between negative pi over 2 and pi over 2, that restricted domain. So you have to be careful, and I like to work it out from the inside out each time. I'm going to give one more example. So like, now if this were inverse sine of sine of, let's say, pi over 3. Well, pi over 3 is between negative pi over 2 and pi over 2. So the identity would hold here. This would be equal to pi over 3. But if we think about it, just working from the inside out, sine of pi over 3 is root 3 over 2. And inverse sine of root 3 over 2 would be positive pi over 3. So the identity would hold for this example as well. All right, inverse cosine, so similar, we'll go through this a little bit faster. Same notations as inverse sine. So with the -1 as well as arc cosine. Okay. So again, if I take the equation here, the inputs are going to be ratios and the outputs will be angles. Okay, if we go back up to where we graphed all of the trig functions, remember cosine, when we restrict the domain to be from 0 to pi, then cosine is 1 to 1. And the domain of cosine was still -1 to 1. So the domain and range flip, meaning the domain of inverse cosine will be -1 to 1, and the range will be from 0 to pi. Now 0 to pi is quadrant 1 and quadrant 2. And cosine is positive in quadrant 1 and negative in quadrant 2. So that you can, if you think about that, that will give you all of the outputs for cosine between -1 and 1, just from quadrant 1 and quadrant 2. Okay, so if we were to pick, I'm going to use the same values for x that I did for inverse sine. So like -1, -√2/2, 0, √2/2, and 1. Well, inverse cosine of -1 would be pi. Inverse cosine of -√2/2 would be 3 pi over 4, right? Because I'm thinking about the range being from 0 to pi. Inverse cosine of 0 would be pi over 2. Inverse cosine of √2/2 would be pi over 4. And inverse cosine of 1 would be 0. √2/2, so just labeling my x and my y-axis. So approximately √2/2. Okay, I'm going to have each tick mark be pi over 4. Okay, and then just plotting those points. Oops. So the graph looks kind of like that. If I show you, I'll show you this on Desmos as well. So y equals inverse cosine of x, okay? And if I were to graph cosine, I think it's kind of hard to see because of the, oh yeah, because of the scale. I have the scales being different. Okay, but if we were to have cosine restricted from 0 to pi, which I can't write on this graph, unfortunately, you would be able to see that the graphs are symmetric about the line y equals to x. All right, so cosine, we've restricted the domain for cosine to be 1 to 1 between 0 and pi, so the range of inverse cosine is from 0 to pi. Let me just draw a unit circle. That's quadrant 1 and quadrant 2. Okay, so inverse cosine of √2/2. Cosine is positive in quadrant 1 for those of those two quadrants. That would be equal to the angle pi over 4. And inverse cosine of positive 1, well, cosine would be equal to 1 at 0. Let me give you another one. How about inverse cosine of negative 1/2? Well, that would be approximately there. And that angle, right, so that's negative 1/2 comma root 3 over 2. That angle would be 2 pi over 3. Okay. Or arc cosine of negative root 3 over 2. That would be 5 pi over 6. Okay, so angles from quadrant 1 and quadrant 2 between 0 and pi. Okay, works the identity here. So when you think about composing inverse cosine with cosine, and cosine with inverse cosine should be equal to x for the domain of the inside function. Works the same as the identity did for sine. Now, 1/2 is between negative 1 and 1, therefore the identity would hold here. But if you want to think about it from the inside out, inverse cosine of 1/2 would be equal to pi over 3. And cosine of pi over 3 would be equal to 1/2. So the identity holds here. Now, negative pi over 6 is not between 0 and pi, right? Not in the range. So the identity would not hold here. So you would have to evaluate this exactly, you would have to think about from the inside out. So inverse cosine of negative pi over 6 would be equal to root 3 over 2. And inverse cosine of root 3 over 2 would be equal to pi over 6. Positive pi over 6. Whereas, let's say we had inverse cosine of cosine of positive pi over 6. Well, pi over 6 is in the range of inverse cosine, or that restricted domain for cosine. But if you're thinking inside out, cosine of pi over 6 is equal to root 3 over 2, which would be equal to pi over 6. But here the identity holds. Okay, inverse tan, same notations. Arctan or inverse tan. Okay, the inputs are ratios, the outputs are angles. Inverse tan, if we go back up to where we restricted the domains of the graphs of the parent functions. Okay, tangent's restricted domain is from negative pi over 2 to pi over 2, and the range is negative infinity to positive infinity. Okay, so that means that the domain of arctan will be negative infinity to positive infinity, and the range will be negative pi over 2 to pi over 2. So you could pick values to find points for the graph. I'm not going to have you guys be graphing the inverse trig functions. If it helps you with understanding them, it's fine. You can figure out what they look like. But the domain is negative infinity to positive infinity, right? So this graph is actually continuous, and then its range is negative pi over 2 to pi over 2. Okay, so negative pi over 2 to pi over 2, but the endpoint's not included, that's going to be like sine quadrant 1 and quadrant 4, but negative pi over 2 and pi over 2 are not included in that interval. So quadrant 1, quadrant 4, 0 is included. All right, inverse tan of negative 1 of those two quadrants, tangent is negative in quadrant 4. Oops. So tangent would be equal to negative 1 approximately there, which is negative pi over 4. Not the coterminal angle, so not 7 pi over 4. Inverse tan of negative 1 is only equal to negative pi over 4. If you type that into your calculator, you will get an approximation for negative pi over 4. Or if you're in degree mode, then you would get negative 45 degrees. And then arctan of 0 would just end up being equal to 0. Okay, or let me give you one more. How about inverse tan of root 3? That's quadrant 1. That would be up here at pi over 3. Okay, the identities work in the same way as sine and cosines. Okay, now inverse tan of 12 would give you an angle whose output, so like tangent of an angle is equal to 12. Well, this represents the angle, I'll call that angle theta, so tangent of theta would end up being equal to 12. The identity holds here. Okay, 7 pi over 6, well, 7 pi over 6 is not in the range of inverse tan from negative pi over 2 to pi over 2. Therefore, the identity would not hold. Tangent of 7 pi over 6 is equal to root 3 over 3. So this is actually equal to inverse tan of root 3 over 3, which would be equal to pi over 6. Positive pi over 6. And let's think about one more. How about like inverse tan of tangent of negative pi over 3? Well, negative pi over 3 is in that range. You could also think about tangent of negative pi over 3 would be equal to negative root 3. Right? And then inverse tan of negative root 3 would be equal to negative pi over 3. So I'm going to pause. I'm going to stop there, and we'll finish looking at the other inverse trig functions in the second part of